Hello! In this video, we are going to evaluate the integral of sine to the fourth of x. Now, it turns out a trig identity that will be useful is the following. This identity. It turns out that this identity tends to be useful when evaluating integrals with sine and cosine where both are raised to an even power. So, how can we apply this identity to the integral we're evaluating? Well, we're going to rewrite sine to the fourth of x as sine squared of x squared. And then we can replace sine squared of x with our identity. So just like that. Now notice we have something in the form of something times something squared. If you recall, when this happens, we can just rewrite this as. So all we had really done is we distributed the exponent across. And now notice, 1/2 squared is really just 1/4. And because 1/4 is a constant, we can pull that to the outside of the integral. So really, this is the integral we're evaluating. Notice it's in the form of a minus b squared. If you recall, when we expand this out, we get a squared minus 2ab plus b squared. So let's apply this idea to 1 minus cosine of 2x squared. So really, at this point, this problem now becomes 3 separate integrals. So really, what I have done here is I have brought the integral to all 3 terms. So really, we have the integral of this minus the integral of this plus the integral of this. That's exactly what we have here. And the entire thing is still multiplied by 1/4, which is what we have here. So this is what we get. Now, the first 2 integrals are actually pretty easy to evaluate on their own. So let's evaluate these 2 integrals real quick. The integral of 1 is just x. The integral of 2 cosine of 2x is just sine of 2x. But now, this integral is a little bit trickier. So I'm just going to keep it as it is for now. I'm actually going to call this integral integral A. And so what we're going to do is we're going to move back up to the top and evaluate this integral separately from the problem. So let's first just move back up to the top. And now we're going to evaluate integral A separately over here. And notice the integral we're evaluating is cosine to an even power. Another identity that tends to be useful in these sort of situations is this one. Now, notice it's not immediately applicable because this says cosine squared of x, this says cosine squared of 2x, right? But instead, let's replace x with u. The reason why I have u is because you can think of cosine squared of 2x as though it says cosine squared of u, where u equals 2x. So really, all I'm going to do is I'm going to replace u with 2x. So as you can see, I've replaced u with 2x. And of course, 2 times 2x is just 4x, so really we have cosine of 4x. So just like that. But what that means is we can now replace cosine squared of 2x with what we have here. Next, 1/2 is just a constant, so we can just pull 1/2 to the outside of the integral. So now, this is the integral we're evaluating. But we're ready to break this integral up into 2 separate pieces. Right, just like that. And these integrals are pretty easy to evaluate on their own. The integral of 1 is just x. The integral of cosine of 4x is just 1/4 sine of 4x. And normally we would add a plus c because this right here is the general solution to this integral. but I'm actually not going to include the plus c here. The reason why is because this is a part of a bigger integral that we're evaluating. So all I'm going to do is I'm actually going to take what we have here and replace it with what we found. And so now, at this point, because we have evaluated all three integrals, we have evaluated this integral completely. So we're ready to put a plus c here. And now let's just simplify this up a little bit. To start, let's just distribute the 1/2 across. Next, notice we can combine like terms. We see that x plus 1/2 x is just 3/2 x. And now we can just distribute the 1/4 across. And so this is the solution to this integral. And so yeah, that's pretty much the idea of how you could evaluate an integral like this. And so yeah, that's pretty much it for this video.